Ja, ich darf jetzt ein ganz spezielles Highlight präsentieren, nämlich den Professor Amnon Luwigsburg von Mobileye. Er wird uns einen Vortrag geben zum Thema die 3 Säulen des vollautonomen Fahrens. Es ist wieder diese magische Zahl 3 und er teilt diese Zukunft des vollautonomen Fahrens in die Bereiche Sensing, Planning und Mapping. Vielleicht sage ich ein paar Worte noch zur Firma Mobileye. Mobileye ist, denke ich mal, Leading Edge im Thema Automotive Bildverarbeitung. Wir haben auch heute gehört, wird er auch von einigen Tier 1s verwendet und eingebaut in unsere Fahrzeuge. Mobileye stattet 10 Millionen Fahrzeuge mittlerweile aus von 25 Automobilherstellern weltweit und ist damit sicherlich Marktführer in der Branche. Und auch Professor Luwigsburg ist über die ganzen Grenzen hinaus bekannt. Er ist Inhaber des berühmten Sachs Chair für Computer Science an der Hebräischen Universität von Jerusalem. Er ist Begründer von Mobileye, hat 1999 diese Firma gegründet, ein italienisches Unternehmen, das auch zum größten Börsengang eines israelischen Unternehmens in der Geschichte von Israel wurde und hat neben seiner Tätigkeit für Mobileye auch an anderen Themen gearbeitet. Er arbeitet nämlich seit 2010 und war auch dabei bei der Gründung von Orcam, einer Gesellschaft zur Unterstützung von Sehbehinderten und Blinden, und hat das Ziel, Abermillionen von Menschen mittels einer unauffälligen Wearable-Plattform doch zum Sehen zu verhelfen. Das heißt, Hightech meets nicht nur Automotive, sondern auch Hightech meets Medicine und schafft auch, ich sage jetzt mal, vielen Leuten zu mehr Glück im Leben. Deswegen freue ich mich ganz besonders heute drauf, Professor Luwigsburg von Mobileye hier zu begrüßen. Herzlich willkommen.
Thank you. Good afternoon, everyone. I'll focus on software in this lecture, and I'll talk about the 3 major elements to making a fully autonomous car. And the way we look at it, we call them pillars. One is related to sensing. Most people have an intuitive understanding what it means to sense and interpret the sensing information. The other one is mapping. What kind of maps? How do we create these maps? How do we update these maps? And how they are connected to sensing? And the third pillar is driving intelligence. We call this driving policy. And this is the reason that we take driving lessons. It is the ability to understand a multi-agent type of scenario when we need to understand human driving behaviors. We need to know how to merge into traffic. So it goes more than just the control theory. It's the high-level decisions, the planning, and how all of this is connected. Right? The main theme of the talk today is that the sensing, mapping, and the driving policy, they must be handled simultaneously. These are not 3 separate blocks, sensing done by company A, mapping done by company B, control driving policy done by company C. It has to be done all together because they influence each other. If you do it separately, then you start raising unreasonable demands on each block. Unreasonable demands meaning that it will never work. By looking at it as one big element, then you can kind of play with the demands and make something that would work. Okay, so this is the main theme of the talk today. So let's 2 slides about sensing, because sensing is the most intuitive part. I want to skip it, even though that most of what we are doing at Mobileye is sensing. So in terms of sensing, the purpose of the sensing is to build an environmental model. And environmental models, where are all the moving objects, where are all the vehicles, pedestrians, obstacles, where are all the path delimiters like a curb, guardrails, barriers, where are all the drivable paths and their semantic meaning. All of this, 360 degrees, is an environmental model. So let's just see what goes into it and what is challenging and what is not. So the first one is all these moving and stationary objects. So first achieve 0 false positive, 0 false negative. 0 false positive is already part of ADAS, but 0 false negative is really what is necessary for autonomous driving. Vehicles at any angle, not just the rear of the vehicle. Pedestrian detection needs to be enhanced considerably because we need to know what the people are doing. Not only that there is a pedestrian there, but is the pedestrian looking at me? What is the pedestrian doing? Where is the pedestrian standing on the sidewalk, on the road? And then general obstacles. The point I want to make here is that this is the easy part. This is a natural growth of driving assist. Okay? I'm not saying easy is maybe not the right word, but it's the natural growth of driving assist. The second element, called this path delimiters, we're talking about detecting the free space where the host car can move, detect any boundary. Boundary could be a curb, a guardrail, a row of parked cars, any boundary, and label the type of boundaries. So I would say that this is kind of the first leap beyond ADAS, but even that is not correct. The Euro NCAP 2018, 2020, they talk about specifications of any boundary, even though they're a bit vague what they mean by any boundary, but clearly it's moving towards being able to infer path delimiters as part of ADAS, part of driving assist. But this is one leap beyond where we are today with driving assist. The third one is really the killer. It is drivable paths. It is understanding where all the drivable paths are, reading all the pavement markings, understanding, connecting the drivable path with traffic signs, associating semantic meaning to each drivable path. Is this path heading to a highway exit? Is the path going straight? Is there a split? Is there a merge? All the stuff that we take for granted when we are driving, these are very, very complicated. And this is not part of driving assist today. Driving assist today detects the left and right lane. That's it. You want to do lane departure warning, lane keeping assist. You don't care about all the rest. This is a very, very big leap beyond driving assist, and this is where most of the challenge exists in going from driving assist today to autonomous driving. Another slide I want to make sure is, why do we need surround camera? So I think conventional wisdom is that you need a front-facing camera. You need to read. There are things that only a camera can do. You need the color of the traffic light. Only a camera can tell you that. You need to read the traffic signs. Only a camera can do that. You need to detect the lanes. Only a camera can do that. So clearly, you need a front-facing camera. But why do you need surround cameras? Because there are many sensory constellations that talk about, say, have a front-facing camera, front-facing radar, 4-corner radars, laser scanners in the front and the back, and you have kind of a 360-degree cocoon. I would say that yes, for highly autonomous driving in highway settings, that's fine. Once you get into city traffic, where things are becoming much more complicated, that is not sufficient, and let me try just to show where things are. So why would we need a corner camera? We need a corner camera first to detect pedestrians when we are kind of turning, be able to detect the pedestrians. This can be done with a laser scanner, let's assume. We need to have a precise boundary of the vehicles, not just knowing that there is a vehicle there, but the precise boundaries of the vehicle. So we need more resolution. And the biggest issue is we need to understand the drivable path. Drivable path is texture. Only a camera can give you that information. So therefore, we need a camera in the corner. Why would we need a camera looking kind of a wing camera? Again, we have pedestrians, we have three-dimensional objects. We need to associate a lane assignment to the car that is on the side. So we need to read the lanes, that's texture. And also the path delimiter confirmation. So the front-facing, understand that there is a curb there. We want to confirm that this curb exists and have the side camera see that curb. And then why would we need a rear camera? Again, we have pedestrians and three-dimensional objects, but we want to have redundancy for the front-facing capability of detecting lanes. So this gives you a 360-degree. So this does not mean you don't need radars and you don't need laser scanners, but you must have cameras 360 degrees if you want to enter into city traffic. So that's all what I want to say about sensing. I want to go into next issue is planning, the driving policy. So I took here something from the internet about, that today's experimental cars, in this case it's Google's, but I think all of them are like that, are too conservative. And they create accidents by being non-human-like driving behaviors. And the point I want to make here is that driving is a multi-agent game. We need to understand human driving behavior in order to merge into traffic in a safe manner. So we need to plan. So here I want to kind of make the point of what is the difference between sensing and planning. So sensing is the present. I have an image, I have a video, and I want to know where all the objects are, where all the path delimiters and so forth. I want to sense the present. When I'm sensing an object, a vehicle, I'm treating it not as a human behavior. I'm treating it simply as an obstacle. So it's sensing the present. It's a single agent game. It's only me in the road. And it's perfectly predictable. That means if you give me enough input-output examples, I can put a machine learning algorithm that will learn how to predict, given an image, given sensory information, tell me where all the objects are. What is the technology? Technology is the deep supervised learning. It's part of machine learning. Today it's very, very popular to talk about that, but this is really the tool of sensing the present. What is the driving policy? Driving policy is planning for the future. It's not the present, the future. It's multi-agent game. It's not only me. It's other behaviors, and these are not just obstacles, they are behaviors. I need to understand them. And I need to ask questions, what will happen if I do this? What will happen if I do that? And it's not perfectly predictable. And the technology behind that is called reinforcement learning. So what is that? You want to learn a policy. You have states, you have actions, and then you have rewards. And you move from state to state by taking an action. Action could be change lane, an action could be slow down, an action could be accelerate. And state is the current sensory state that you are in, and you are getting a reward. What makes this going into the future that the instantaneous reward is not what you really want to optimize. What you want to optimize is the accumulated reward, something that goes accumulated into the future. So say, for example, I want to exit in the highway, and I know that the exit is 3 kilometers away. I can start changing lanes, and all of this gives me zero reward. But the reward that I'm really interested in is, do I successfully exit the highway or not? So you're looking at something really accumulated into the future. And the learning process is, you observe a state at time t, you decide on an action, you get a reward, and you move to state number t plus 1. Okay? In supervised learning, actions do not affect the environment. Therefore, you can collect a lot of training examples and build a optimal policy from state to action. In supervised learning, the effects of the actions is local because we're not accumulating rewards. And given the correct answer, in supervised learning, we're always given the correct answer. We have an input and output, and the output is always correct, and therefore we're training a learning algorithm. In reinforcement learning, because of the reward, we're not always given the correct answer. So it's a more complicated problem. This is it's part of a paper that we wrote, is about our algorithm for doing reinforcement learning using a recurrent neural network. The gray box there is a piece of a network that is then replicated over time. And there is a state going into an action, and there are 3 deep neural networks there that are building the capability. And let me show you some examples here. So this is a toy example just that we get the idea of what does it mean to plan ahead. So the idea here is that the red box here is a car entering into a roundabout, and the roundabout is busy, so you need to squeeze in. And there are 2 types of behaviors in the roundabout. There are the blue cars, which are aggressive. Once they see you try to squeeze in, they'll accelerate, not want to let you. In Israel, it's very, very common. That's all the drivers are like this. Okay. And then the green cars are more relaxed. They see you squeeze in, they'll slow down. Now, the point is that the red car, the agent doesn't know about that. All what he tries to do is to squeeze in and creates accidents. And these accidents are the negative rewards that he tries to optimize. And this is how it looks after the agent has learned. So you'll see that you saw the blue box accelerating, and you see that the red one is squeezed in incorrectly. Okay? So this is a rather difficult problem because it's something that's difficult to do in a rule-based type of thing. Let me skip this slide. Okay, now the point is, why are sensing and driving policy really coupled together? Why not have sensing, company A, driving policy, company B, have expert do the sensing, have another expert do the control? Why are they coupled together? They coupled together because what is known as abstraction. So if we want to build a system where receiving sensing information on the left-hand side, in this case I simply wrote video, but it could be additional sensing information. And then we take the big problem of sensing and we break it down into modules. In this case, these are different deep networks. One does object detection, the other one does drivable path delimiters, and so forth and so forth. You break down the problem into components, and then you have another deep network that will do this driving policy. Now, this part of the abstraction, this breakdown is kind of obvious from an engineering point of view. You have a big problem, you break it down into its component. But what about the driving policy? How do we decompose this into modules? Now, in the area of reinforcement learning, this is called temporal abstraction. So the idea is the following. In an end-to-end system, right, we want to learn a policy, and this is the pie on the left, that takes the sensing state, takes also a state of things that we want to remember from the past, and maps it into control parameters. Say only 2 parameters, accelerate and steer, left or right. Okay? So you have all the information from sensing, and then you map it onto your control. This is not good. It means you are not breaking it down. Breaking it down is called temporal abstraction, is that you're building a policy not directly to the control, but there are all sorts of, you can think of this also as a hierarchy. Are you in a highway? Are you in a rural road? Are you in an urban setting? Do you want to take over? Do you want to follow? So first you want to make this decision. Once you have that decision, you go into another hierarchy of another policy and so forth. So you're breaking down these policies. So you can see now how these two are connected. Because in order to do the right policies, you need to break down the sensing into many, many parts. So you cannot have one company doing the sensing, the other one doing the policy. It has to be done together, either through a very, very strong collaboration or have one company do both of them. Okay? Let's go, as the last 9 minutes that I have here, let's go into mapping. Okay? With mapping, the situation also needs a definition. Right? So with sensing, we know what sensing is. There are cameras, radars, laser scanners. With mapping, we humans do not need a map at all. So why do we need a map? Right? There are navigation maps. These are the existing maps. And then there's the high-definition maps. The TomTom and Here and others are talking about high-definition maps. And then there's the Google three-dimensional cloud of points type of map. So when we talk about mapping, we have to decide what do we mean about mapping. And then there is localization. If there's no map, we don't need to localize ourselves. In a navigation map, a GPS is sufficient. A few meters of accuracy is enough. But when you talk about high-definition maps, you want to use the maps in order to do control. The accuracy has to be centimeters. So when you talk about maps, we have to define what it means, what it means by a high-definition map, and then we have to figure out how to localize, because the GPS would not give us this kind of accuracy. So when we look about what are the requirements to enable autonomous driving, we see first it has to be the update has to be a continuous process. Right? I don't care how we build the map. The real issue is how do we update this map. Now, if this map is safety critical, because we're doing autonomous driving using the map as redundancy to path information to drivable path, using the map to get foresight, to know where things are going ahead beyond sensing, this is safety critical. If it's safety critical, it has to be correct all the time. It has to be correct all the time. The update should be done continuously. Okay? So if an update done continuously, it has to be crowdsourced. I don't see any other way of doing continuous update without crowdsourcing. If it's crowdsourced, then the data per vehicle per kilometer should be very, very small. We are talking, what I'll show you, about 10 kilobytes per kilometer, so that we can send it through existing communication infrastructure like 3G, LTE. And finally, because we are in the automotive industry, we want to be very, very low cost, right? So we want to use existing infrastructure. what is the existing infrastructure? Cameras are in every car or will be in every car because of the safety regulations, the driving assist. By 2020, 2022, there's no reason that every car will not have a front-facing camera. So this is something that is already there regardless of autonomous driving. Second, communication from car to cloud is also something that is coming regardless of autonomous driving. So let's take these two elements and use them to build the maps without adding any new hardware. So the idea is to build a concept where the 3-dimension is sparse. Sparse meaning that we're looking only for landmarks. We're not representing 3D in a detailed manner. And we're representing the road. The road is a one-dimensional type of information. The lanes are one-dimensional information, and those we are representing them in a dense manner. And therefore, we can put this together in a very, very low bandwidth, this 10 kilobytes per kilometer. So in terms of a landmark, we're talking about visual landmarks. And in the next slide, I have here a list. We're talking about signs, rectangular signs, triangular signs, all sorts of traffic signs, road markings, traffic lights. Here we're talking about more than 20,000 different, a vocabulary of 20,000 different items. And then poles, reflectors, horizontal structures like bridges and tunnels and so forth. Anything that is fixed in the world is a landmark. We use these landmarks to fix the location, the localization drift. So here's an example in somewhere in Germany, just to get a sense of the density of landmarks you can get. Okay, so in this case, these are pavement markings and traffic signs and poles and so forth. And in terms of density of landmarks, if we include lampposts and reflectors, we get, in the worst case, it's about 200 meters, the maximum distance between landmarks. Okay? This is important because you need to have high density in order to fix localization drift. And then what we do, the information from the camera builds the environmental model, builds the lanes, and we call this harvesting. This is on the clip that you see. The camera stitches all this information, uses ego motion in order to put everything in the same local coordinate system, and then uses the landmarks to fix localization drift. Just to get an idea of this ego motion. Today, ego motion has evolved to becoming something very, very accurate. This is a comparison between the ego motion and a 30,000 euro INS. So it's very, very accurate system. And the ego motion is right there all the way compared to a $30,000 inertial sensor. And then all these packets are sent to the cloud, and then they are integrated into a high-definition map that we call a roadbook. And the roadbook has 3 usages. One is to localize, because we can use the landmarks to localize. HD map content. It can enrich existing HD maps, or it can replace all the concepts of existing HD maps. And then you can use it to actuate control using map content. So let me show you some examples. So this is a localization. You see the landmarks, and you see the point here in terms of localization. All this map has been built by several drives in this area. This is using it for control. So what you see here, these lanes are not by sensing. This is taking the map and projecting it onto the image space. And it's so good that you think this is sensing, but it is not sensing. Let me show you a bit more. Here is a Nissan demo that was in San Jose, January this year. It's a complicated city driving, 15 kilometers of urban driving. And what you can see here, the point is the 3 points. These are the control points that the system would provide. And you can see that it runs in areas where sensing would find it very, very difficult, like in a turn. You don't see the lanes in a turn. And this mapping concept, what enabled the demo to work well. This is another demo in March, again in Japan. Here's again, the point here is this 3 points, the control points that are outputted by the system. But you can see the complexity of the driving. This is really city traffic driving. Enabled by these kinds of map concept. This is a proof of concept activity we're doing with Volkswagen, building now maps in complicated areas. This is, for example, in a junction. This is looking at a 28-kilometer route here in Germany. And this is the projection of the map on Google Maps. So this gives you an idea of some idea of accuracy. Right? So you see that these colored lines are more or less on top of the Google Maps. Right? So we get accuracies of centimeters here. This is the route that is being taken. So this is the using it for control. So you can see that we're using it for control because these two lines here, right? Sensing cannot detect these two lines because of the obstruction from the vehicles. But as we go forward, you'll see that these are exactly on lanes. I think we'll see that more or less here. Yeah, you can see the lane markings. Right? So again, this is the projection from the map onto the image space. And you can see how accurate it is. And here again, you can see that you get the foresight. That you saw that the lanes here, see how foresight, this is foresight, this is not sensing. So you can clearly see this is a projection from a map and not sensing. Again, these are complicated areas as part of testing that we're doing. And last 5 seconds, so I was kind of on the spot. So to summarize, the point I was making here, I didn't talk about hardware, I didn't talk about the chips, IQ chips, central computing of the car and so forth. Those are very, very interesting topics to talk about and critical topics to talk about. What I wanted to point attention is that there's more than sensing going on here. And the other things that are going on here are not easier than sensing, and in some cases are even more complicated than sensing, especially the driving intelligence, the driving policy, and also how do we manage the mapping? Because without managing the mapping, we will not have autonomous driving. Because we need the map for redundancy, we need the map for foresight, and it has to be continuously accurate, therefore it must be crowdsourced, and this has to be handled. And I showed some examples of what we're doing there. Thank you.
So, thank you very much for this insight. I think it's everything underway. I think we don't need to care that we never will have autonomous driving. So, therefore, that leads it to my question. By when do you think will all this technology, all this sensing and mapping and intelligence and deep learning and technology lead to the situation that the car will be more intelligent or more suitable as a driver, as a human driver? So when do you expect for the future? When will the year when this will happen?
Okay, so it depends whom you ask. If you ask Uber, they'll say 2018. If you ask Elon Musk, he'll say 2017, 2018. My feeling is that the right time is somewhere 2020, 2021. Mm-hmm. And I think this is also the common wisdom in the automotive industry. And I believe that the automotive industry is going to that path. Mm-hmm. And I believe that by 2020, 2021, we will see from the automotive industry full level 4 cars and shared mobility using these kinds of concepts and these kinds of technologies.
Mm-hmm. And this is something which is not so far in the future. I think from now on 5 years.
Yeah, in our business, it's tomorrow.
It's almost tomorrow in terms of our development processes and so on. And I think if we install all these online update capabilities, crowdsourced information collected in some backend and some servers, and if you join all this data and bring that exchange this data and bring it together, I think we can fulfill this proposal.
Yeah, the mapping stuff that I showed, we're already planning with some car models early 2017 to start sending this kind of data. And we have activity with our German car industry starting 2018 to send this kind of data. So by 2020, 2021, I'm pretty sure we'll all have very, very good and accurate maps that could be updated continuously.
Okay.
I cannot hear.
Wait for a moment for a microphone.
Yeah, I was just wondering, what is the density you expect of percentage of instrumented car you need to be able to have a certain reliability output of the mapping?
So we believe that it's around 8 cameras around the car to provide a 360-degree awareness. And definitely you need a front radar, corner radars, and at least front and rear laser scanner, say a Scala type, Vallejo Scala laser scanner, or the second generation laser scanner would be fine. Front and rear, that should suffice. But I also believe that it's very important for the entire industry to reach consensus on this matter, so that we all agree on what is the sensor constellation around the car, so that we all prepare ourselves to the next phase in which we have autonomous cars, and standardization will protect everyone in terms of liability and so forth.
So we still need strong collaboration in the industry, I suppose, in the starting setup of sensors, I suppose, and as you said, and also the interfaces.
I think the interesting thing that the consortium with here, although it's mapping, really started a more kind of strong collaboration, at least in the German industry. I see much more talks between car manufacturers after this consortium was built than before. And I think for autonomous car, this kind of collaboration and communication is critical to reach standardization.
Any other questions?
Okay.
No further questions. Thank you very much for this impressive talk.